Hello. Hello, Sanjay.
Yeah, yes. Now I can hear you. Yeah. Okay. Just 1 second. This screen share option is enabled, right? You have that option.
Yes.
Yeah. Okay.
I can see that.
Okay. So we will start after. Okay, let's start. It's already 10:30. Okay. So yeah, just 1 second. Very good morning to all the participants. Today we have with us Dr. Rishikesh Sahay as the guest speaker for this session. Before he start his talk, let me take the privilege to introduce him. So Dr. Rishi is currently working as a software OT security engineer at Ørsted in Copenhagen, Denmark. Currently, he is working on cyber risk assessment and compliance according to the IEC 62443 and NERC CIP cybersecurity standards to protect the offshore wind power plants. Moreover, he is a certified IEC ISA 62443 cybersecurity professional. Previously, he was working as a product security architect at Man Energy Solutions in Copenhagen, Denmark. He did his postdoctoral research at the Technical University of Denmark. At that university, he was involved in a project entitled Cyber Resilience for the Shipping Industry. He completed his PhD from University of Paris and Marie Curie in France in 2017. His PhD thesis was focused on autonomic cyber defense using software-defined networking. His research interests include cyber risk assessment and mitigation, IoT security, automatic cyber defense, software-defined networking, and cyber resilience. So with this small introduction, I hand over the session to Dr. Rishi.
Thank you very much, Sanjay, for the introduction. I will share my screen.
Yes.
Can you see the screen now?
Yeah, it's visible. Yes, please make it full screen. Yeah, please go ahead.
Yeah, thank you very much, Sanjit, for the invitation and for the nice introduction. I will talk about the software-defined networking and the security risks and attacks that is very prevalent in the SDN environment, and some mitigation mechanisms that have been proposed to protect the software-defined networking environment from these cyber attacks. And first, I will also talk about the traditional networking and what is software-defined networking and why we need that, and what are the problems in the traditional networking environment and which led to the invent of software-defined networking, and some threat vectors on SDN environment and some mitigations which have been proposed to address those threats. So in the traditional networking, routers are embedded with the some high-level purpose, like they have the control plane functionality, and all the intelligence are embedded in these routers, and they process the packet and they forward based on those rules. And forwarding functionality is also there in these routers, and forwarding is done based on the installed rules in those forwarding tables. So here the control plane and data plane are very tightly coupled in this traditional networking environment. So there have been some problems in these traditional networking environment. Generally, network administrator need to configure the switches and routers manually using some low-level commands. And to do that, they should be aware of low-level device-specific syntax to configure or deploy the policy in the switches and routers. So those policies or syntax which they need to be aware, they are very complex, and they need to be very much aware of those syntax to configure those switches and routers, which lead them to learn those syntax and then to do the deployment. So this also makes it very time consuming generally to deploy those rules and policies in those switches and routers, because first it also needs to be deployed manually. So moreover, decision making is very much distributed in this legacy network environment. Different nodes in the network do not have knowledge of global status of what is going in the different part of the network. They are not very much aware about that. So it also leads to suboptimal decision making in this traditional networking environment. Moreover, it also introduces extra delay in mitigating attacks if attack happens, or if there is some problem because of some network failure, or because of some too much congestion in the network. So it also leads to some extra delay in mitigating attack or diverting the traffic because of some network failure. Or even if we have to deploy some redundant network resources, in case of failure, it causes some extra delay. So for instance, if a switch is not working properly, or if there is some link failure, first it takes time to detect those problems in the network, and then it introduces some extra delay to deploy the or redirect the traffic to another part of the network, because we are not aware about what is happening in the network, or there is lack of intelligence in the networking environment that other routers or some system which deploy those rules, they lack those awareness or knowledge what is going on in the network. So that causes some delay in mitigating the attacks. And there have been a report from Juniper that causes that in that they have written that most of the network downtime is caused by like manual network intervention by the network administrator. First, then it requires manual configuration of those switches and routers, so it causes extra delay and causes network downtime. So routers and switches, moreover, it also causes that routers have become very much complex, routers and switches, because we need to deploy too much rules there, and also those rules are very complex, and they need to handle all those packets which are coming in and getting forwarded through those routers and switches. So it makes them very complex and too expensive. Moreover, in the legacy networking, like security applications or devices like firewalls, NAT, or intrusion detection systems, they are statically deployed in the network. So we need to be aware like where we are going to deploy those firewalls or NAT devices in the network. So all these things need to be planned, and then they need to be statically deployed, which also introduces some delay to those legitimate traffic which are which are getting forwarded through those devices. All the traffic which are going through that link, they need to be processed through those firewalls or NAT devices or intrusion detection systems. So it also causes a delay to those legitimate traffic. So these are some of the challenges in the traditional networking environment. So those challenges led the researchers to think how we can handle those challenges or address those challenges more effectively. So that led to the invent of software-defined networking concept, and it evolved to tackle all those challenges of the legacy networking environment or traditional networking environment. So as we can see in the figure, in the SDN control plane, which is this part, is decoupled from the data plane. And most of these routers and switches which are connected in the data plane, they form the forwarding devices. They are also called as forwarding devices. And control plane, which is this part, is centralized at entity, which is called the SDN controller. We also call them as a SDN controller. So as we can see in the figure, controller communicates with the data plane through this southbound interface. I will introduce all these terms later on. And through an interface which is called the southbound API, and through which they communicate. And applications such as firewalls, NAT, and other networking and security applications, those are deployed at the application layer, which is this part of the SDN environment, and they are deployed at the application layer of the controller. And this SDN technology provides logically centralized control. As it is connected with the data plane devices and manages these devices. So all these routers or switches, or even we can call them forwarding devices, are connected through this southbound interface to this SDN controller. And SDN controller can monitor, we can deploy some applications at the application layer of the SDN controller, which can leverage this advantage and provides the global visibility in the network. So centralized controllers offers like global visibility, as it is connected with all the data plane devices and controls them. The global visibility enables the network administrators or network operators to deploy the applications which can take the optimized decision based on the global status. So we can deploy some applications which can leverage this benefit of having a southbound interface from SDN controller to these forwarding devices. And based on those informations, those applications which we deploy can take the optimal decision and deploy the rules if there is some network failure. So this mechanism provides the global visibility, and we can leverage that to do optimal decision making in the network. So for instance, if a switch is flooded with the malicious packet or a link is congested, then controller can deploy the rules at the switches to filter that traffic. For example, let's say if this link is not working, SDN controller can infer that this link is not working, so we can divert all the traffic which is going through this link through this link. So, or if this switch is not working, it can infer that if it is not responding to the query of the SDN controller, then maybe after a while it can infer that this switch is not working, so we can forward the traffic to another path. Or if they detect that malicious traffic is coming through this access switch environment, then SDN controller can deploy the rules to block that particular kind of traffic which is malicious at the access switch itself in the network. So moreover, this SDN environment offers programmability in the network. We can deploy the applications at the controller, as I have said, which can program the switches automatically. So also the network operators can express the network and security policies at the application layer of the network. And those high-level policies can be translated into low-level open flow rules based on the status of the network. So here, network operators or network engineers can deploy some high-level policies, like let's say if a traffic is coming from host A and it is going towards host B, and if it is FTP traffic or any kind of other traffic, we can express those policies in a very fine-grained level or even at the very high level. And so that kind of traffic should be blocked. So based on the rules, I mean, when the packet comes, this switch will forward the first packet to the SDN controller, and based on the policies, controller can deploy the rules to block or either forward. That is based on the status or high-level policies which are expressed by the network operator. And all these things can be done automatically in an automated way, which also avoid too much manual intervention caused by the network operator. And they don't need to be aware of those low-level device-specific syntax to deploy those rules. So it also is the task of network operators. So these are some terminology that we use in the SDN context, like forwarding devices. As I've said, these are the hardware or software-based data plane devices. So it comprises of switches and routers, and they are interconnected. And data plane is interconnected forwarding devices. So all those switches and routers or hardware firewalls or intrusion detection systems, they which are deployed in that with the forwarding devices, they are called the data plane. And southbound interface is the interface between the forwarding devices and the control plane. As I have shown here, this is the southbound interface. So it is an interface between this SDN controller and all these forwarding devices. And control plane is like a entity at the application, rests at the application at the controllers, which form the control plane. And northbound interface is interface between the application layer and the controller. So the this interface, which is between the network applications or security applications and between the SDN controller, that interface is called the northbound interface. So key attributes of the SDN is like it provides logically centralized controller. Data plane devices are connected to that centralized controller, and it provides global visibility in the network, as SDN controller can monitor all the traffics, and also it can decide to deploy the rules based on the traffic conditions. And it also offers programmability. Data plane devices can be controlled by the network or security applications which are deployed at the application layer of the controller. So it offers programmability, which also is some task of the network operators. And applications that uses the SDN services are abstracted from the underlying technology. They are not aware of what kind of devices we have, or where we have the middle boxes on like firewalls or IDS. So all these applications are abstracted from the underlying technologies. And forwarding decisions in this SDN environment can be taken on per flow basis rather than on the packet level. So I'm also giving a brief introduction about the open flow switches, because it is important part in understanding the SDN security and different applications. So it consists of one or more flow table which perform packet lookups and forwarding. It has an open flow channel to an external controller, which is also southbound interface, we call it. And communication between the controller and the switches occur via open flow protocol. We call it open flow protocol. So general format is like match fields and counters and actions, which is part of this open flow table. So match fields, I will introduce it here. Like match field can be of ingress port or IP5 table, like source IP, destination IP, protocol, or other like other things. Also we can use VLAN ID, MPLS. And there are three high-level actions which we can describe in this open flow switches, like forward, block, or modify. So forward is general actions, which is to forward the traffic. Like if traffic is coming from host A and going towards host B, and everything is normal, then we just forward the traffic. Or if a traffic is coming from like host C and going towards host B, and we think that that is malicious traffic, then we can block that traffic in the open flow switches. So that is another actions. And then the modify is we can divert the traffic, or we can modify some header field also in the open flow switches. So that can be based on maybe some network conditions. So this is the basic SDN operations. Like here, a traffic is coming from host A and going towards host B. And when the packet comes, if it matches, then it is forwarded to the host B. And the first packet, it is forwarded to the SDN controller. and the SDN controller will decide whether we need to forward that traffic based on the policies deployed at the controller, or we need to block that traffic. So if here it has decided that we need to forward that traffic to host P, so it introduces the action forward here in the SDN switch. So the benefits are like, now it is easier to program the network and security applications by leveraging the programmability of the network. We can program the firewalls, rules, or NAT applications at the SDN controller itself. And applications can take the leverage the global visibility of the network provided by the SDN controller, and they can deploy the rules like configuring the network devices. For example, if a firewall rule can be configured at the switch automatically from where a malicious traffic is entering in the network. Moreover, it becomes simpler and less error prone to modify network or security policies through high-level policy language as compared to the low-level device-specific syntax. So we can deploy those high-level policies, and network operators don't need to have the very much knowledge about the low-level device-specific syntax. So we can deploy those policies, and decisions can be taken based on those high-level policies, and rules in the open flow switches can be configured based on those high-level policies. So it also causes less error in the network environment, and also avoids the manual intervention caused by the network operator, which we can automate that task. So this is a general traditional networking versus SDN environment. So here we can see in the conventional networking or traditional networking, or even we can call it legacy networking, we have the statically deployed firewalls or intrusion detection systems, or deep packet inspection box, and it causes delay to legitimate traffic. If a traffic is going through this link or through this link, or it can cause the delay to those legitimate traffic, even if we know that the traffic coming from this machine or host A is legitimate one. It can cause the delay, because all the traffic needs to be processed by these middle boxes, which are statically deployed in the network environment. However, in the software-defined networking, we can deploy those applications or these functionality at the application layer of the SDN controllers. So based on the environment or status in the network, which can be inferred thanks to the global visibility provided by the SDN controller, these applications at the application layer can configure the open flow switches through the southbound interface provided by the SDN controller, and policies or rules can be deployed dynamically, which provides flexibility that if we know that a traffic which is coming from a machine A and going to machine B in the network, and which is legitimate, they don't need to be processed by these statically deployed middle boxes in the network. And it also causes like fast processing for fast forwarding, we can say, in the network, which can reduce the delay. So these are some I have talked about the benefits provided by the SDN environment, but it also introduces some threats in the SDN context. If we have the SDN controller or SDN network, there are a lot of threats like forge or fake traffic, and it can be triggered by like faulty devices or a malicious user in the network or external to the network. And attacker can use the network elements like open flow switches to launch attack traffics such as DDoS attacks against open flow switches. And here we need some kind of solutions, and which can be based on some authentication mechanism, or some IDS can be a solution. Also, there can be an attack on vulnerabilities in the switches, and it could be used to drop or slow down the packets in the network, or like switches, these open flow switches can be used to deviate the network traffic. So here we need to monitor and deploy the solutions to monitor the network and detect abnormal behavior in the network. Also, we can like deploy those monitoring applications at the near the access or entry point in the network. Or also there is a threat on attack on the control plane communication, which is southbound interface between these SDN switches and the controllers, and it can be used to generate DDoS or DOS attacks for data theft. So here we can use the TLS or SSL can be used, and trust model between with multiple trust anchor can be used. So that is very much specific to SDN environment, this control plane attack on control plane communications. And there is also threat on like attack on SDN controller itself. And if SDN controllers are compromised, it can lead to the compromise of whole network, and whole network can be stop working. So most of the like this is the severe threat in the SDN environment, and it could like lead to compromise of the whole applications or whole environment. And here what we can do, like the replication can be one solutions to, and also to detect or remove or mask normal behavior. Even replication is not a very good solutions, because if one controller is compromised and we have just replicated that, it can also be compromised. So we need some kind of diversity of controllers also. Those controllers should have different applications, and they need to be configured differently. They need to have different security mechanisms. So with some diversity and replications or redundancy, we can minimize this threat, because just deploying the redundant controller doesn't provide any benefit, because as I said, if we compromise, attacker can compromise just one controller, then it is not a very difficult task for them to compromise the redundant one. And also we need to have like a trust between like applications which are deployed at the application layer, and also the controllers. So in this lack of ability to establish trusted relationship between the applications and the controller, it all is also one of the challenge in the SDN environment, and autonomic trust mechanisms can be used here. Also, there are vulnerabilities in the administrative stations or the management plane, and it exists in also the traditional networking environment. So like strong authentications we can use to address that threat. And also like lack of trusted resources for forensics and remediation. So here we need to allow to understand the cause of a detected problems, and here logging and tracing can be used to minimize this threat. So now this is the more about like what are the threats which are very specific to SDN environment and which are non-specific. So threat vector one, which is about forge or fake traffic flows here, that is not specific to SDN, and it is also a threat in the conventional or legacy networking environment. Vector 2, which is attack on vulnerabilities in the switches, this is also a threat in the traditional networking environment. So the threat 3, which is attack on control plane communications, that is specific to SDN context, and here communication with logically centralized controller, which happens through the southbound interface between the data plane devices and the controller, that is very much vulnerable to attack. And also SDN controller itself, which is the controllers, that is also very specific to SDN context. And if SDN controllers can be compromised, then it can lead to the compromise of whole network and whole applications deployed there. And also we have the threads, which is applications deployed at the SDN controllers or at the application layer and between the controllers. So that is also very much specific to SDN environment. So controllers should there should be some trust relationship between those applications at the application layer and between the controllers, and that should be some kind of authentication also. And threat vector C, which 6, which is attack on vulnerabilities in the management plane. That is not very specific to SDN environment. It is also prevalent in the legacy networking environment. And also the vector 7, which is a lack of trusted resources for like forensics and remediations. This is also not specific to SDN environment. It is very much prevalent in the traditional networking environment. So now I will present some problems, or we can call it attacks in the SDN environment. And one of them is like DDoS attack, which is very much prevalent in the network, and it can be happen through like multiple channels. And these DDoS attacks can compromise the whole network, or if it is like huge amount or attack size is very large, then it can lead to compromise of the whole network. Even if we have solutions, it doesn't matter. So in DDoS attacks, like attackers can try to flood the victim network or switches or the controllers or the link connecting victim network with the internet with bogus traffic. And the main aim here is to like exhaust the network resources or the link or the switches. So the current trend in the DDoS attack is like 42% of these DDoS attack is the volumetric DDoS attack, which the main aim is to just exhaust the network, and it is very much prevalent in the internet today. And attempt main aim is to consume the bandwidth within the target network or between the target network and the rest of the internet. Then another prevalent attack is a state exhaustion attack and the application layer attack. So a state exhaustion attack, they tries to exhaust the flow tables in the switches using TCP IP protocol. And the application layer attack is at the, also very much prevalent, and it is and these reports are have gathered from the this Urban Network report, which is worldwide report on cyber attack trends, and more they are very much specific to DDoS attacks, and they also provide some solutions to mitigate those DDoS attacks. So application layer attack is also at the applications deployed on the internet, and it can be through the HTTP. So here I will talk more is very much specific to DDoS attack on control planes. And here we can see that this is an example in which malicious attackers can send a huge number of unknown packets or bogus packets to the switches. And if the switch doesn't find the rules in its flow table to handle those packets, then it will forward those packets or traffic to the SDN controller. And that can keep, and it can keep sending these packets to the controller. And thus controller and switch keep themselves very busy in this environments. And this leads to like control plane saturation attack. And all the legitimate traffic will be dropped from here. So here we can see in the figure, like this attacker can send the malicious traffic or packets or bogus packets to this switches, and then the switch will keep sending all those traffic, and it can be like it can send many different packets. And then this channel also between the switch and the SDN controller will be busy, handling those requests, and then it can lead to legitimate traffic which is coming from this machine and going to this machine. It will be dropped and it won't be handled properly. So that can cause this control plane saturation attack. And there have been some solutions proposed to handle this inherent communication bottleneck that arises between the data plane and the control plane because of control plane saturation attack. So to address this challenge, there is a framework which is called avant-garde that have been proposed to, and this is in this framework, there is an extension of open flow data plane, and they have introduced and they call it connection migration, and they have tried to introduce some intelligence in the data plane itself to so that we can avoid the uh, like not all the traffic needs to be forwarded to the controllers. So moreover, this actuating triggers that we can see are also introduced to enable the control plane to expedite both of detection and also responses to the changing of flow dynamics. So the aim of actuating trigger is to enable the data plane to asynchronously report network status to the control plane. So this data plane devices will report the status to the control plane, and moreover, it can be used to activate a flow rule if under some certain predefined conditions to help the controller manage network flows without delays. So here we can see it more specifically. Like here we have deployed some intelligent rules in the data plane, and when a host send the packets, and if it matches, then it will be forwarded or it will be blocked, and those can be based on these conditions. And so conditions will be checked, and then the predefined rule will be activated, and it will also notify the controllers about the status of the network. So here we can see this like a host is sending some traffic to host B, and this is a TCP sync packets. So first in the first step it will send, and then this switch will send some the data plane device will send some sync ACK back to the host A, and then in the third stage again it will send the TCP ACK, and then this data plane device will report about this traffic to the controller in the control plane, and then there will be some response from the control plane, and then the migration stage will be triggered, and that will lead to like TCP sync sent from this data plane to the host B, and then again sync ACK, and then TCP ACK back to this host B, and then the communication will be happen between this host A and host B, and that is called the relay stage that will happen between the hosts. So here we try to like not forward all the traffic back to the controller, and we avoid and address that challenge of control plane saturation attack, and we deploy some intelligence in the data plane itself to handle many status or many packets in the network automatically, and it will report back the status to the controller, and controllers can then also intervene, and they can deploy some rules based on the status provided by the data plane devices, or it can activate the rules in the switches if it is there, and that can also mitigate some other challenges. So this is another DDoS mitigation solutions provided by the hardware, and it is called defense flow. So here the aim is of this tool is to protect the data center network of companies from DDoS attacks. So controllers can program open flow switches, which are here, to behave as an open flow counters, and which collects flow statistics and forward those flow statistics back to the SDN controller. And and we also try to make a baseline of the profile or flow statistics or network traffic here, and all those can be monitored for anomalies related with the DDoS attacks. And if attack is detected based on that, like we have some baseline profile at the SDN controllers, and it will be monitored periodically. And if the SDN controller detects that there is some anomalies or malicious traffic in the network, then it can program this open flow switch, and or it can deploy a new rule which will divert all those abnormal traffic or malicious traffic back to this defense probe, which is an applications or deployed by this hardware, and then it will process all those diverted suspicious traffic or malicious traffic. And if it finds that the traffics are normal, or it is clean and it is not malicious, then it will sends back the clean traffic back to this open flow switches, and then it will be forwarded to the controllers. So here it protects, basically it is deployed at the access switch in the net in the data center network, and all this diversion take place at the entry switches itself, so that we can avoid congestion in the middle of the data center, middle path in the data center network. So this is another solutions to for DDoS detection and mitigation, and it relies on some neural network techniques such as self-organizing map to detect the attacks, and detection application is deployed at the controllers. And flow collector here is an application which collects the flow statistics from the open flow switches and forward it to the feature extractor module. And then the feature extractor modules extract the features from the those statistics provided by the flow collector. And these extracted features are forwarded to the classifier, which is here self-organizing map. And then it which compares it with the baseline traffic which it has. And if it finds some deviation, then it issues some security alert. And it so it relies on features such as, for example, average packet per flow, average bytes per flow, or average duration of per flow in the switch, open flow switches itself. So then those alerts can be it provides the alert back to the attack alert module, and then the controller can deploy the rules in the switches to block the traffic, or if the operator wants that it should be diverted, then it can deploy those policies that those traffic will be diverted or redirected to some further middle boxes or some other applications which will further process those suspicious or malicious traffic. And after those traffics are cleaned, or if it finds that it is not malicious one or suspicious, then it will be forwarded back to the normal path. So this is also another solutions to handle the DDoS attacks in the SDN environment, and it uses bidirectional sketch count algorithm to detect the attack, and it identifies the destination IP with high. Basically, it relies on this destination IP with high asymmetric communication pattern based on threshold value. So bidirectional sketch count algorithm. So if from A, this which is the open flow switch or access switch here, it is collected if attack is identified for a victim like B, then it is the controller, like all the traffic from this A is forwarded to the S flow collector. And if it identifies that there is a traffic or attack traffic for the victim V, then it programs the switch and forward all those traffic through applications which further process or filter those traffic, and then it is blocked or it is redirected, or even if it is cleaned, then it is forwarded back to the normal one. So this is another low rate flow table attack. So here it overflows flow tables of switches by like generating minimum number of packets, which can degrade the network performance. So it consists of two phases, like probing phase and attack phase. And in the probing phase, it infers the network, attacker tries to infer the network configuration of flow rules in the switches with some small number of probing packets. So attacker sends some probing packets and tries to analyze the response back from the SDN open flow controller as SDN controllers. And then based on that, it infers what is the network configuration in the switches. For example, it will send of probing packet with various field values in the packet headers to measure what is the response time of the SDN controller. For example, let's say it sends the first packet and it measures that there's a return time of T0. And then again, it changes some header fields in the packets here. And then it measures what is the return response time. So let's say that is T1. So then if T0, that is the previous response time from the controller back to the adversary or malicious user, if it is greater than the T1, which is the change header field later one, so it can infer that the change header field is not in the SDN switches or in the open flow switches. So with this mechanism, it tries to analyze what type of rules in the open flow switches are deployed. And if T0 is it is same as T1, then in that case, both are not in the set of match fields in the open flow switches. So with that type of probing stage, it tries to infer what are the what type of rules and what are the match fields mentioned in the open flow switches. And then based on those analysis, it launches attack traffic. So each attack packets can then it can generate that each attack traffic or packets will trigger a unique rule installations. So here, what can be the solution? We can introduce some artificial jitter during the delivery of the very first few packets. If if a first packet is coming from any machine, we can introduce some extra delay in that, so that to avoid this kind of analysis by the malicious host. So controller does not generate a flow rule for a new flow or new packet immediately. Once it receives, it introduces some jitter or delay in providing the response. So it will wait deliberately for a random time, and then it will send back the response. So it will then it can handle this type of attacks, like the analysis which is done by the malicious host to launch the attacks. So yeah, this is the solutions that I just told, that SDN controller can generate some artificial delay during the delivery of the first few packets, and does not generate flow rules for a new flow immediately once it receives new packet in message. And also we can for dismissing the attack, we can introduce some throttling of the very high rate traffic which is coming from the hosts, or even if it is a legitimate one and we are receiving very high traffic rate, then we can just introduce some throttling. So this is another solutions to handle the DDoS attack in the SDN environment. And the solution, they named it drop bridge. So here they introduced that different internet service providers can collaborate to mitigate the attack traffic. So for example, let's say DDoS traffic is coming from some external host here, and it is going towards this machine here in the ISP2. And this is the C1 and C2 are the SDN controllers, and these are the switches here. And once it detects that or DDoS attack traffic is coming from some devices or from some machines external to its network, then it will send the notification. This machine will send some notification to the controller, and this ISP controller will establish a connection with this controller in another ISP network. So for this controller to controller communications, we can have some kind of applications, and we can also use another control plane channel, which is not the part of the normal data plane traffic. So that we can avoid, like if the controller is sending some alert message or some to mitigate the attack traffic, then those will not be dropped, because it is using another control plane channel to share that kind of sensitive information. And then based on the alert information provided by this controller C2, this controller C1 in the ISP network can deploy the rules directly in the access switches in the in its network to mitigate those kind of attack traffic. So here idea is like detection will be done by the end host itself, because they are best in the position to detect what kind of traffic is good for them and what kind of traffic is bad. So detection is done at the end hosts, and then if it detects the attack traffic, then it sends the notification to its controller, and then this controller will send some kind of alert information, which can be agreed between the collaborating ISPs, that this should be the format of the alerts, security alerts. And so based on that security alerts, this controller will just deploy the some rules here, and it will mitigate the that kind of DDoS traffic directly at the access switches. So it will avoid like congestion in the network in this ISP network also, because the rules are directly deployed at the entry points, and it will avoid the collateral damage caused to the legitimate traffic. And moreover, here this ISP or this controller should not be aware what kind of underlying technologies or underlying switches are there in this ISP. So it also protects the privacy of these ISPs somehow. And they are because they have been agreed on some particular security alert formats, and if this is the alert, then this ISP will just deploy the rules in its access switch environment to mitigate the traffic. So there is also forwarding loop attack, and loops can cause DDoS or network attacks, and packet travel from one node to another without reaching the destination. So here we can do some header space analysis and policy check, which can be performed to detect this network loop problem also, which is also a very common forwarding loop attack. There's also a policy violation in the SDN environment generally. Like here we can see that there are two hosts, H1 and H2, which are sending some traffic to the external internet. So here, for example, H1, which is sending the traffic, and it is getting forwarded to the NAT devices, and H2, which is sending, it is forwarded to the NAT and then to the application firewall. So these NAT devices can modify the packet header fields like source IP or destination IP from this host. So if it says that, let's say we have the rules here, which says that H1 traffic from H1 or H2 should be just sent back to the internet. But since it has been modified here, So this switch cannot infer that this is the traffic from H1. So it can lead to some kind of violations because of the modified packet header fields, and which is very common in the SDN environment, because sometimes we can have the rules in the switches which is not synchronized with the policies at the SDN controller itself. So there's can be some lack of synchronization between them, and which can cause the policy violations in the SDN environment. And because of that, the traffic which should not be forwarded to the external internet, or the traffic which is coming from the external internet should not be forwarded to some protected server, can be like uh, uh, past the those secure mechanism or policies in the switches, and getting can be forwarded to those targeted servers. And also another is like some kind sometimes we provide the cached version. So here, for example, H2 is getting some cached response from the XYZ, but here we have this is access control rate limit, and here we need to block the traffic from H2 which is going to for XYZ. But there can be a scenario where it is getting some cached response. So cached response should also be subject to the access control restriction. It should not get those cached response, and rule says that it should be blocked. So we should access control and rate limit also those cached response. So there has been some solutions proposed to handle these kind of policy violations, which they call it like a flow tags architecture. So here, what we do, we introduce like traffic which is coming from H1 and H2. We introduce some tags in those traffic. So based on those tags, the rules will be deployed in these switches. Like if traffic is coming from S1 here, like we can see at the switch S2, it will see the tag. What is the tag? And based on tag, it will forward it to the access control rate limit. Or if traffic is coming from access control rate limit, and if tag is, for example, 4, it will be forwarded back to the S1. Or if the traffic is coming from the access control rate limit, and the tag is just random anything apart from this 4, then it will be forwarded back to the internet. So this type of tags in the packets that can help to minimize this kind of policy violations, which is very common in the SDN environment. So we introduce tags sometimes, like if a traffic is coming from H1 and it should go, for example, to host P, and it should be like pass through the firewall, or it should go through another path. So we just introduce some kind of tag, and based on tag, the core switches in the network, they can forward the traffic, or they can be like further processed by firewalls or intrusion detection system. So even if the packet is modified by the middle boxes such as NAT devices in the network, based on those tags, we can just forward the traffic correctly to the destination. It will not lead to some kind of violations that controller says that we need to block the traffic from H2. It should not go to XYZ. And based on some modification which is done by NAT devices, we are those packets are getting forwarded to the destination. So this type of flow tags helps us to like introduce to address these kind of policy violations, which is caused by the lack of synchronization in the controller and at the data plane. There is also some misconfigurations in the SDN environment. For example, here we can see this is the OpenFlow controller. And if traffic is coming from 10.0.0.2 and it is going to .3, and then we need to modify the source IP to 10.0.0.1. That is the policy at the controller. And if traffic is coming from 10.0.0.1 and it is going to this destination .3, we need to modify the destination IP to .4. So this is some random policies. And also, if a traffic is coming from 10.0.0.1 and it is going to .4, then we just need to forward. So these are the policies at the controller, and they are deployed at this open flow switches. But here, traffic is coming from 10.0.0.2, and that should be that is going to 10.0.0.4. So we need to block that. And here, traffic is coming from, this is the rule here, and at the firewall. And then another traffic is coming from .2, and it is going to .3. And because of this policy, we are modifying the packet header actually to .1. So if it is modified to .1, then it says that the traffic to 10 dot coming from 10.0.0.1 and going to 10.3, it is destination is modified to another IP which is .4, and it is forwarded back to the 4. So here, because of this misconfigurations, we are forwarding the traffic back to the destination which should be blocked. So this is a problem in the SDN environment, which is caused by misconfiguration. This is also some kind of policy violations, we can call it. So here we need to we need to correctly plan what kind of policies we will have at the controller, and what type of policies we will have at the middle boxes such as firewalls, or even at the SDN switches. What kind of modification will be done by the switches or by the NAT devices, and we can introduce some authorization roles. So this is like a control channel attack, and there are some 3 possibilities, like man in the middle attack on the open flow connections, or there is a attacker can compromise the link between the controller and switches. And moreover, malicious user also can impersonate those switches to the controller, and also a controller is impersonating to switches. So attacker can impersonate as a controller to the these network devices, and or it can impersonate as a switch, legitimate switch to the controller. And this is man in the middle attack in the open flow environment. So which provides the attacker full control over open flow switches, and it is very realistic because of we have the in-band network channel. And here we can introduce some kind of mutual authentication or TLS to protect this type of attack, or and address those threats. So then it can be there can intelligent rules for timeout, or this is the information disclosure, and intelligent rules for timeout or randomization can make it difficult for sniffers to understand the network pattern. As I have previously presented this threat, that we can introduce some jitter in the network environment where SDN controller is responding back to the adversary. And then a monitoring tool also can be deployed, which can detect the difference in the response time between sending a new and existing flow rule. And all rules here are proactively installed by the network administrator. That can be a solution. And also we can have an intelligent counter, which method can also be effective in making fake responses based on some time and based on the nature of the network attacks. There can be also threat of repudiation, and can be that denial by one of the party involved in communication with other party. And here we receiver needs to verify the packets that are sent from the actual sender, and sender needs also to verify that packet sent to the actual receiver included in the packet header. So here solutions can be like, we need to first audit and log all type of network activities. So that can also be a challenging task, to have the audit and logs of all the network activities, and for which can also causes some kind of processing overhead on the controllers, or even in the switches if we are doing that. So we need to be very careful in analyzing what type of tasks, or what type of logs we need to have, which are very critical. And here also we can have the transport layer encryptions, and also some third party verification, which can address this repudiation threat. There can be also like the tampering, which is like a deliberate or unauthorized modification of network information. So strong policy checking can be deployed before packets or flow rules are installed to avoid any conflicts. We can deploy some policy check like for the packets before deploying the rules. And also we need to check the conflict between flows rules in the open flow switches, and also the firewall rules, which is either deployed as a high level rules at the SDN controller or in some devices. So we need to check is there any conflict between these rules in the firewall and also in the open flow rules. And we can also have auditing and monitoring, which can be distributed across several network points. Of course, it is not in the real environment, it is not possible to have the response from all the data plane devices, and which is reporting status back to the controller. That can be too much overhead on the SDN controller in the real network environment. So we need to think like, from which points we can have the response to address the scalability challenges. And like, controllers should manage and routinely check legitimate connections. And this is elevation of privilege, which can be also a threat in the SDN environment. And attacker here tries to gain privilege to access the system and application. That is, they try to bypass the access control. And so we need solutions can be like to provide some privilege on flow basis rather than user basis. Like, we don't provide, we should not provide privilege like all the traffic from host machine A should be forwarded to the host machine B. So here we need to have some fine-grained policies or rules, like what type of traffic from host A should be forwarded to host B, not all the traffic. So we need to decide on per flow basis rather than this user level basis. And flow insertion in the switches are should also be like authenticated, but of course it can also increase some overhead. And moreover, we can also have some kind of like verification at the switch also for all the packets, to avoid this elevation of privileges. And this link between distributed controllers, that is also one of the threat when we are having a controller to controller communication. So this is also called as east and west communication in the SDN environment. So here, like, we need to have some kind of synchronization. There can be some lack of synchronization between the controller to controller communication. So we need to have some kind of interface at the SDN controllers to provide the communications. And if we are communicating with some other network, controllers in another network domain, then we need to have some kind of service level agreement. And also one solutions can be to have a separate control plane channel, which is not used for normal data forwarding, which can like protect those controller to controller communications. if controllers have to share alert information or some kind of mitigation, some kind of information to mitigate some attack traffic. So this controller to controller communications also like needs to be authenticated, that the controller A should know that the traffic coming or the communication is initiated by controller B. It is not by some adversary. So we need to also have some kind of mutual authentications. Like controller B should also be aware that it is communicating with the controller A, which is legitimate one, not to some another controllers. So there are a lot of challenges in the controller to controller communication, and there can be some kind of solutions based on like authentication and authorizations also, and also like separate control plane channel for communications. So like I've said that out of band control channels can be used for distributed controller to controller communications, which is not used for normal data forwarding. And also like authentication mechanisms can be deployed for controller to controller communications, like both controllers should be authenticated to each other. They should know that they are communicating with the legitimate ones. And there can be also attack on the vulnerabilities in the management plane, which is also very common in the traditional networking environment. So here, if a management plane is compromised, it can lead to compromise of the whole network. So here we can have some monitoring tools which can like regularly monitor the status in the network, and also we can have the authentication, a very strong authentication, which can be a solutions that a legitimate user is accessing the network. So these are some of the solutions which is also used in the traditional networking environment to monitor the whole network, or the like have some kind of monitoring at the critical junction in the network, or some kind of a strong authentication also that a legitimate network operator or user is accessing the network. So yeah, these are some of the security threats that I have presented, and some of the solutions to address those threats. And thank you very much. If you have questions.
So thank you, Dr. Rishi, for your nice presentation on SDN and the research issues. So dear participants, anybody, any questions related to his talk? Hello, any participant? Yeah. You can write in the chat box also if you.
Hello.
Hello.
Yes, sir. Please, sir.
Yeah.
Please ask your question.
Yeah. Thank you, sir, for nice talk. So my question is that what is the role of incident response in this case? If some containment strategy part happens, then is there any strategies for that handling such type of ongoing attack for the vulnerabilities?
So what kind of vulnerabilities you are asking for? Like, is it to protect the SDN environment, or like to some kind of incidents response to mechanism to mitigate the attacks using SDN, or just to like attacks which happens on the SDN environment?
Yeah, just attacks to happen. Yeah.
Okay.
Yeah, just attacks to happen for that. So if in case of incident response, that's I'm asking.
Yeah, incident response is very important in this context, I would say. because at last we need to if we are using the SDN, of course we need to leverage the advantage of southbound communications, and also we can deploy those incident response mechanisms at the controller. We can deploy some policies or applications there at the controller, at the application layer, and those can be like it can monitor like in those incident response mechanism. For example, let's say it is deployed as an application which we call it for let's say application I, and then we have the monitoring mechanisms which monitors all the traffic, legitimate or malicious one, and if it detects that there is some anomalies or abnormal traffic, then it can sends the information to those incident response applications or mechanisms that we have deployed there. And based on those alert informations provided by the monitoring tools that we have deployed or monitoring applications at the controller, in those incident response mechanism, we can have all the security policies to mitigate different kinds of applications, different types of attacks. And based on the security in alerts which has been triggered by the monitoring application, that incident response applications can analyze that security alert, and then it can inform which type of rules we need to deploy. So we are deploying the incident response. We can deploy the incident response as an application there at the controller, and then based on the threat in security alert information shared by the monitoring tools, it can deploy the rules using the southbound interface in the open flow switches to mitigate those kind of traffic. So here I would say, yeah, it is important, the incident response mechanisms. We need to have that kind of incidents response mechanism, even if we are protecting we are talking in the context of SDN, securing the SDN network itself, or also using SDN to automatically mitigate the attack traffics. In that case also, it is very efficient that we can have all the security policies and network policies in those incident response applications, and based on some monitoring informations, those can be deployed in an automated way, which can also like reduce the downtime caused by the manual intervention by the network operator.
Yeah, and there is another scenario that, for example, let us consider an use case. So, if system configuration is changed during means runtime, and so how to analyze that? Is there any component is vulnerable, like in system configuration change? So, if such type of use cases, so is there any methodology to check like that how configurations is affected, means maybe any vulnerable component has been added in the new configurations?
So if dynamically at a runtime we are system configurations changes, then we need to have some kind of we can address that with some kind of applications deployed at the controllers in the SDN environment, which will monitor all the status of the configurations changes. For example, let's say in the particular use case, if status if the configuration of a machine A changes, it will detect that there is some changes in the configurations. Or also we can have some kind of agents in the system itself, which will trigger to the controller directly if there is some kind of changes in its configurations. And based on that information from those agents which are deployed in those systems, we can at the controller we can decide what to do, whether it is legitimate changes or we need to like isolate that machine because there is some abnormal changes in that configurations. So maybe we can deploy some kind of agents there directly, or is at the controller we can have some kind of applications to monitor those. We can define the policies or there in some applications which will just query the different machines, critical machines especially in the network, and check whether there is some changes in its configurations.
Okay, thank you, sir. Thank you.
Yeah, Dr. Rishi, like suppose some of the participants, if they want to start research in SDN and open flow switch, like the DOS attack that you mentioned, then is there any simulator by which they can start working and they can check how the performance is enhancing?
Yes, we can use this RU SDN controller in the Mininet, and also which is very well managed RU SDN controller, and also we can use this HPing tool to simulate those DDoS traffic.
Okay. And okay. Yeah, can you?
In the Mininet, we can use this
Mininet.
Yeah, in the Mininet, yeah,
Mininet,
which is a emulation platform to emulate the this SDN environment actually.
Yeah, and then suppose we implemented it in Mininet, and then we need to generate a attack traffic, right? So that we can test whether the scheme that we are proposing will protect against DOS attack or not. So how do we generate the attack traffic?
We can use the HPing tool.
Okay.
Yeah, it's HPing which can be used to generate the attack traffic. And there is also botnet simulator Bonsai. Yeah, that can also be used.
Okay, so yeah, okay, then anybody else, any questions?
Sir, I'm Revati from SRM. So actually I'm doing my research in SDN and DDoS attack only. I tried that using a single controller, it's DDoS mitigation and prevention is easiest one, but using a multi-controller, if I need to add a camouflage node in the multi-controller, just I'm doing in the form of a clustering and classification. So for each cluster, if I need to allocate a controller, so in that time I'm having some problem in the implementation. Can able to tell some tools for that? Can I actually add a camouflage node in that? How can I able to add camouflage node in each and every cluster?
So you are using different SDN controller for each
using
clusters.
Same type of. First, I tried with the different type of controllers, and then I tried with the same RU controller. 5 controllers I assigned, implemented. Using Mininet only, I created a topology. For each controller, I assigned 64 hosts. So in that time, instead of a single controller, in my objective one, I used only single controller. After that, I'm using a multi-controller scheme. So in that time, how to avoid the traffic flow. So
if I correctly understood your point, you want to, in the multi-controller environment, you want to avoid the traffic, but what kind of traffic it is?
So using HPing 3 commands, and then those things only, I creating a traffic, a random traffics, and then I'm forwarding those things. So for each, now I created a cluster. In that cluster, shall I place a camouflage node instead of detecting node? Instead of it is going to a controller, shall I control the detection here itself in the data plane itself?
Oh, yes, you can do that detection in the data plane itself, but here we need to be like careful in the sense like not to put all the intelligence or detection mechanism directly in the data plane. Of course, we need to have some kind of optimization that you can use, like what should be the optimization level. Because if you will put all the intelligence in the data plane, that is, yeah, of course, solutions. But then in that context, there can be some comments or criticism, like then what is the use of SDN environment? So maybe you can also like use asynchronously sending the reports from those data plane where you have deployed those detection back to the controller, so that controller should also be aware of the status in the in its network, because that will provide some kind of balance. And here you can also like think for some optimization mechanisms, like to have the optimization or optimum level, like optimize the resources in the network, like where to deploy the those kind of detection mechanism in the network, and what will whether we it will be optimum to deploy at the controller or in the data plane. So that can also be a thing that you can think for.
Okay, sir.
Okay, thank you, ma'am, for your question. Anybody else? Any other question? No? Okay. So with this, I conclude this session, and thank you, Dr. Rishikesh, for your nice and informative lecture on SDN and DOS attack. And I also thank you because you joined since morning 7 o'clock, because you are in Denmark. So thanks for that. And thank you all participants for joining this session and attending his talk. Thank you. Thank you one and all.
Thank you, Sanjit, for inviting me for the
Thank
talk. And yeah, it was nice
Thank
talking
you.
to you and all the participants.
Yeah. Thank you.
Thank you very much.
Thank you. Thank
Bye-bye.
you. Thank you. Bye. So, dear participants,